So I have a kinematics problem here. It's a projectile motion problem. It says a ball is thrown horizontally from the top of a 20-meter high hill. It strikes the ground at an angle of 45 degrees. With what speed was it initially thrown? So at first this may seem like a pretty tough problem, but it actually lends itself to some really good intuitive thinking once you draw a picture of it. So let's say we kind of have our hill, looks more like a mountain here, but you kind of get the idea. So we'll draw, this is a height of 20, and it's going to be thrown horizontally, so we kind of have the projectile almost going like this, and it hits the ground at an angle of 45 degrees. Okay, so what do we know about angles of 45 degrees? Well, if you look at this, you kind of see that you could make a triangle out of this. And if we know anything about 45 triangles, their lengths are going to be identical here and here. And this is basically a reinterpretation of the problem, except keep in mind our trajectory is going to look more like this. But honestly, like this, the hypotenuse is not really what's important. The important part is that we found out how far in the y direction this ball is going to travel before it hits the ground at an angle of 45 degrees. So when it comes to any projectile motion problems, you want to treat your x and y as independent. If you try making them, if you try making them too dependent early on, it gets very messy. So the easiest thing that we can solve for first is the time it takes for this ball to fall. So looking at this, if you'd like to, you can pause and try this problem out yourself, just with the knowns that we have here. But I'll continue on with how else to solve this. So we're going to solve, we have our change in x, which is 20, and that's going to be equivalent to our initial velocity times time plus 1/2 acceleration times time squared. Okay, so what's our initial velocity? Well, keep in mind we're working with the x-axis here in order to find time, because the key component here is that we have gravity. We can figure this out if we have gravity. We can't just go straight into the y-axis. So our initial velocity, that's just going to be 0. So VO of x, that's just 0. Because relative to the x-axis, this ball is essentially being dropped and is under the influence of gravity, because it's only being thrown in the horizontal direction. That's the direction it's being thrown, and it's only arcing because of gravity. So that means we can set up an equation, essentially 20 equals, I think it's zeroed out, plus 0.5 times 9.8, which is acceleration due to gravity, t squared. And when we take this, essentially what we get is the square root of 20 over 0.5 times 9.8. That equals t. And then correspondingly, t then proceeds to equal 2.02, which if we're accounting for the sig figs that we're working with, we'll call that 2 seconds. So that's roughly how long it takes for this ball to fall that distance. So now we can work with the y-axis, because now we have a time that we can work with here. So if we look at our kinematic equations, this is really all we have here is a distance equals rate times time problem. we just have d equals rt, or if you want to represent that in the notation we're using, you have like the change in the y-axis equals the initial velocity in the y-axis times time, because the velocity is going to remain constant. So that means that our initial velocity in the y-axis is equal to the final velocity in the y-axis. So we don't have to worry about acceleration because we're not accounting for things like air resistance in this kind of problem. It's very idealized. So essentially, we know that our change in y, if we look at our picture, is 20. So that's going to be 20 equals our velocity y times 2, which therefore this ball was thrown with an initial velocity of 10 meters per second.